Here we're going to start from truth tables and we're going to develop optimized or near optimal Boolean equations and corresponding digital circuits to go with them. So the first truth table that we're going to start with is here. And we have 3 input variables and 1 output variable v. So let's go ahead and try developing the first Boolean algebra equation. So remember, each row represents an AND minterm or AND gate, and we need to OR them together. So let's start with the first one. V equals D prime, E prime, and F prime. D prime and E prime and F prime, because we need to invert the 3 zeros, and 1 and 1 and 1 becomes 1. Next, we'll look at this entry here. D equals 0, so we invert the D. We AND it with E, which is not inverted because we expect it to be 1. And then we AND that with F prime because F is required to be 0 here. Our next term comes from this row. D is 1, so we don't invert that. E is 0, so we invert. F is not 0, so we don't invert. Finally, we look at this row here. D is 1, so we do not invert with a prime. E is 1, we don't invert. F is 0, so we have to invert that for this term. So V is equal to 1 if and only if this is true, or this is true, or this is true, or this is true. If any of these four terms are true, then V is true, where true being equal to 1. So let us look at this Boolean equation. If we put this together into a digital circuit right now, we would have a large number of gates, but there is some optimization that we can do. This term here can factor out a D prime F prime and combine with this term. We can also factor out an E F prime to combine with this term over here. So let's use idempotency to duplicate it. V equals D prime, E prime, F prime. We're just rewriting this term here. Now we're going to use idempotency to write this twice. D prime, E, F prime, ORed with D prime, E, F prime. Then we're just going to copy the remaining terms. D, E, F prime. Copy this one. And then we're using the commutative property to write this term last. So D, E prime, F. So let's factor out a D F prime from the first pair, or D prime F prime rather. D prime F prime ended with E prime or E. Then we will OR that with the next pair of terms where we will factor out an E F prime. So we will have E F prime ended with D prime or D. And then we'll just copy this last term without changing it. D E prime F. Let's take some more space. Now we know that this is equal to 1 and this is equal to 1. So by our Boolean algebra theorems, so let's simplify. Equals D prime F prime ORed with E F prime ORed with D E prime F. Now, it may look like it's hard to simplify this further, but there are some tricks that we can use. First of all, let's factor out this F prime from these two terms. This may be the most obvious one. F prime ANDed with D prime or E. Now here's a very interesting detail. The D and E prime and the D prime or E terms are very close to each other. D, E prime, F. So let's do some gymnastics here. We can apply De Morgan's law to this term. So let's do that. We will factor out the inversion, so to say. So we have F ORed with D ANDed with E prime prime. And then we will OR that with D, E prime, F. Now, how did we take this? How did we do this? Let's check our work. So we have F ORed with D, E prime, and then we prime that. So let's first distribute the prime to the internal terms. So we get F prime ANDed with D, E prime, prime. So this OR changes to an and we distribute the prime here and here to the two internal terms. We can also apply De Morgan's law a second time here. So we have F prime, F prime ANDed with here, and now we have F prime or ANDed with D prime or E quantity. This is what we started with in the first term here, so it checks. Now we have an interesting detail here. This DE prime and this DE prime. It seems like it's hard to combine these two just based on our current construction, just using the Boolean algebra laws. However, if we used a system of equations where we substitute K for DE prime, then we can substitute K into V and say that we get F ORed with K primed, and then we OR that with K and F. Right? Now, let's use De Morgan's law here. This is equal to F prime and K prime, and that's ORed with K and F. Now we have a very interesting system of equations here, right? Because our simplification, we get F XNOR, or F equivalence, K. V equals F equivalence K, where K equals D ANDed with E prime. So how do we draw this? Let's draw the optimal circuit that we have been able to develop. So we'll have D, E, F, now, what do? We can say that we need E prime and we put that through an inverter. And now we need to develop k. That is done with an AND gate. We take D and E prime, and now we XNOR this value of k with F. We have a 3-gate solution. Now, what is interesting here is that we went through many different steps of simplification using Boolean algebra. Using idempotency, we had to make the Boolean equation more complicated, which would have led to an even larger circuit to achieve this level of simplification. Recall from another lecture, if you have had the chance to view it, that logic minimization for multi-level logic, which is applied here, is very hard. Two-level logic minimization, NP-complete, and multi-level logic minimization is even harder. So it can be very difficult, but what is nice is that we can come to near optimal solutions by using a minimal amount of work. So just using a basic conversion from the truth table to a Boolean algebra equation, we can do this. This equation gives us 4 AND gates, 3 NOT gates, and 1 OR gate. This is a total of 8 gates. Coming down to this equation, it is significantly smaller. Perhaps 3 AND gates, 1 OR gate, and 2 NOTs. So here we have 3 ANDs, 1 OR, D prime, F prime, E prime. Oh, we have, I'm sorry, 3 NOTs. So that is a total of 7 gates. Any optimization that you can do is an improvement. So just play around to try and get the optimal gate. Let's place our output V here as well. Let's use this as our second example here. So we have 3 terms where G is equal to 1. So G equals, for this term, equals 1, where for this term A is equal to 0, so A inverted, and B is equal to 0, so B is inverted, and C equals 1, so C is not inverted. For this term here, A must be equal to 1, and B must be equal to 0, so we invert the B, and C must be equal to 0, so we invert the C. For our third term, we OR this. We say A must be equal to 1, and B must be equal to 0. Whoops, sorry. A must be equal to 1, so it's not inverted. B must be equal to 0, so the B is inverted. And C must be equal to 1, so C is inverted. Notice that we can factor out between here and here, we can factor out an AB prime term. Between here and here, we have the B prime C term. So we must take this and use idempotency to duplicate it. G equals, let's place it in the middle and write two copies of it. A prime B prime C, or A B prime C, or A B prime C, or A B prime C prime. So for the first two terms, let's factor out a B prime C, ANDed with A prime or A. We will OR this here, and we'll factor out A B prime from these two terms here. A B prime C or C prime. Therefore, G is equal to B prime and C, or A B prime. We can factor out the B prime now and make it smaller, or B prime ANDed with A or C, like so. Let's draw our simplified circuit. A, B, and C. And now we need to invert the B to get B prime. Now we need to take the OR operation of A C, so A or C, and then we combine that with B prime through an AND gate. This gives us our output G. So we have 3 gates. This example uses a 4-input truth table, so we have significantly more terms here. So let's solve for y. Y equals what? I prime j k prime l. Because I is 0, j must be 1, k must be 0, l must be 1. Let's look at this term. I j prime k prime l. Then we have this term, I j prime k l prime. Then I j prime k l, and our last term I j k prime l. So we have 5 minterms. So how do we solve this? We can factor out I j prime k from here. And we can factor out I j prime l from these two terms. What else do we have? We can factor out I from a lot of these terms. J k prime l is another one that we can factor out between these here. What else is available? Well, let's start. Since this can be combined right here with I for these three terms here, and it can also be combined with this first term. Let's use idempotency on it first. So we have I prime j k prime l, ORed with I j k prime l, ORed with I j k prime l. Let's call this quantity inside here q, and so we'll OR with q for now. So this is a temporary variable. So let's factor out the j k prime l equals j k prime l I prime or I j k prime l or q equals j k prime l or I j k prime l, or, and let's substitute back for q, I j prime k prime l, or I j prime k l prime, or I j prime k l. Let us now factor out an I from the last four terms. Prime l, ORed with I and we have j k prime l ORed with j prime k prime l, ORed with j prime k l prime, ORed with j prime k l. Now we can combine these two terms by factoring out a k prime l. And then we can combine these two terms by factoring out kl prime, or kl, or j prime k rather, I'm sorry. This quantity is equal to 1. This quantity is equal to 1. So, what do we have here? Write our output variable y is equal to j k prime l, ORed with I and k prime l, ORed with j prime k. So we have a 4-input variable Boolean algebra equation. Now, it may be possible to simplify this further, and I invite you to play with your Boolean algebra theorems to see if you can simplify it further. It may not be possible. It is a difficult problem to get full simplification. Let's draw the digital circuit for it. We'll draw I, J, K, and L. Now, how many of these signals are inverted? J and K are inverted, so we need two inverters. J, K, L. First we label, and then we need two inverters. One for K, and then we'll get one for J as well. So we have J prime and K prime. Starting from J, we connect J prime. Remember to be consistent with your connections. So if you place the inverters out of order, then be sure to watch your connections. So we have J prime and K prime, like so. Now we need an AND gate here for J, K prime, L. J, K prime, and L. And we need an AND gate for K prime and L. So we'll attach this to K prime and L. And then we can connect J prime and K to an AND gate, like so. J prime and K. Now we need to OR K prime L with J prime K, like so. This needs to be ANDed with I. Like so. And then we can OR that quantity with J, K prime, L. And we have our output Y. This gives us a near optimal digital circuit.